All right. So today is the 4th of August already. We have 2 weeks left in class, which is amazing. Um, so Friday, I did an awful lot of grading and solutions and stuff. So all of that stuff should be posted and available for you to look at. Here are the quizzes and the homeworks that you turned in alphabetical order as always. I'm going to skip today necessarily looking at the solutions because they've been posted all weekend and I tried to make them very complete. There is one question that I'm going to take a look at real quick because one of the online students pointed out that I was going a little fast and it was a little late and I was a little sick of it and made one mistake on the very last problem. So I want to clear that up so that kind of it's set. I think people did, on the quizzes, people did pretty well. The one, I think there were a couple of problems that definitely should be addressed that I saw a couple of times. One was to make sure that as you're doing the arithmetic on these things that your capacitors need to have a negative J impedance. It's negative J over omega C. So make sure that you stick that into your calculator right, or you do the calculations by hand properly or whatever to make sure that you get the proper values. For the other thing, when I told you that the circuit operates at 60 hertz, that is not omega. Omega is 2 pi times f. 60 hertz is I guess a linear frequency as opposed to a radian frequency. And so a few people did the problem based on 60 hertz frequency, and that's not going to give you the right numbers. The final thing was to make sure that you keep your real and your reactive impedances separate. You can't just say, well, I got this magnitude of 754 on the inductor and combine it with the value on the capacitor, or just combine it with a resistor and bring it down to a wholly real impedance. That's not going to happen. So exam tonight, 6 to 7:30 in ERC 214. Online students should already have the exam and the proctors have the password. It was emailed off earlier, so you should all have that stuff. So before we jump into the AC power stuff, I'll go look at this one question number, it's number 10 or 779. We'll look at that real quickly. I'll show you where I messed up, and then I'll entertain any questions that you guys have before we do the exam, or before we jump into the AC power stuff. So, so just so that if you're looking at the solutions or you're looking at your homework or whatever, the circuit that was presented to you in 779 just looks like this. So there is, oops. So there's a 2 ohm resistance here, like it presents has any effect on the problem whatsoever. And it wants you to find the voltage V of t with respect to time. And so this is obviously a second order circuit. The one thing that I know that we talked about, at least briefly, was the fact that for the first half of the problem, getting into the steady state and trying to figure out what the initial conditions are in this circuit, we do just a very mild amount of circuit analysis. And we say before this switch actuates, there is a voltage source, a resistor, and a capacitor. And based on what we know about a capacitor, it acts as an open circuit during steady state DC conditions. Well, if it's acting as an open circuit, then no current is flowing, so there's no voltage across the 2 ohm resistor, and everything, all of the 12 volts is across the 1/400 farad capacitor. So there's 12 volts across that, and that gives you your first initial condition, that the voltage across the capacitor times 0 plus, and this is one of the places where I screwed up, is 12 volts. So that's one of your initial conditions. The second initial condition that we need is the current through the capacitor. And this is where I screwed up, trying to go too fast and not paying attention closely enough to what I was doing. When I look at this, I say, well, with the circuits in this configuration, there is no current flowing through the capacitor because it's a short circuit, or it's an open circuit. And so I solved the problem with I of C equals 0. But that's not right. You're supposed to look at the initial conditions at time equals 0 plus, or just after the switch changes. So we're looking at a circuit where we know that there's the capacitor, there's the resistor, there's the inductor, and they're all sitting here, and we know that there's 12 volts across this capacitor. And one of the other things that I kind of did was I said, well, the current through the inductor, or the current through this capacitor can't change instantaneously, and so it's going to stay at 0. Well, that's not right. The current through an inductor can't change instantaneously. The current through a capacitor, that's fine. It can change like that. And you can definitely have the current in a resistor changing instantaneously. And so if you have put 12 volts across this, then there's also going to be 12 volts across the resistor. One thing that will still be true is that the current running through the inductor still has to be 0, because it was isolated from any kind of source up here, so there was no current running through it, and the current through that inductor, that can't change instantaneously. So if we look at what is the current through the inductor at time 0 plus, that's 0, but let's see, put it this way. The current from the capacitor plus the current from the resistor plus the current from the inductor should all equal 0, KCL at the top node. We know that this is 0, and so the current through the capacitor will be the negative current through the resistor, which is just going to be the 12 volts divided by the 10 ohms. So when you plug all of that in, you should get, you've got negative 1.2 over 1 over 400 equals d1 plus minus alpha d2. We had previously solved that alpha was 20, d2 was 12 based on initial conditions. When you do all of the rest of this stuff, you'll find that d1 solves to be negative 240. And what I had in the solutions was positive 240. So that's a correction you'll need to make to the solution manual for that. And my only excuse is that I was getting really sick of this. It was 8:30 on Friday in the evening, and I really wanted to be doing something else. I wanted my weekend to be starting rather than not ready yet. But so, are there any questions on any of the topics for the exam? To be honest, I'm almost a little worried that I wrote the exam too easy. That's my impression. Is I try either I think there's 5 numbered problems, and so and everything is a very simple and straightforward example of the problem type that it's supposed to represent. So I don't think that it should be a stressful experience for you, but you never know. We try, but if you do have questions, I'm going to stick around for a while today, but for because of coming back and stuff, I'm gonna go home for a little while. If nobody shows up by about 1 o'clock or so, I may head home as early as that. But if you want to make sure that you stop by and talk to me about something, let me know, or stop by early or whatever. Otherwise, I'm gonna go home and do something fun before I have to come back and do the exam. So. If nothing else, I have to go to a bike shop and see how much it's going to cost to have my bike fixed after really, really stacking it up on a hill in Copper Harbor. And it was, yeah. On the other hand, I can strongly recommend that every time you go out and you ride, you wear a helmet. Because there are no marks on my head, but my helmet. It doesn't look very marked up either, but I know that I smacked my head on some rocks pretty good. So, anyhow, lecture 8. We're going to look at AC power, which is one of the. I think it's not an altogether uninteresting aspect of electrical engineering, and in some ways you might think about it as almost being like the original electrical engineering. We're trying to figure out how to quantify the power that's being delivered to a complex load, and that's the kind of thing that is obviously very practical. You have lots of everywhere you look, you see these outlets, and all of those outlets are delivering AC power to gadgets that are plugged into them, and the the load of those gadgets are characterized in lots of different ways. And we'll look, I think, to some extent about some of these things, but it gets more interesting as you start thinking about these devices and what kinds of loads they present to the power system. Things like refrigerators, vacuum cleaners are heavy inductive loads. Things like lights tend to be more just resistive loads, but it's interesting to think about that, and especially when we get into the power factor and power factor correction, that is hugely important because it has very financial ramifications for companies. I even had a student last summer, as we were talking about power factor correction, he got curious. He was an online student. He got curious. He went and he talked to his boss and said, "So, do you know what our power factor is?" And he ended up spending a big chunk of the rest of the last couple of weeks of the summer doing power factor correction. So the concepts that we'll actually talk about in this lecture are instantaneous power, because we'll actually find that there's 3 different kinds of AC power that are worth discussing. Instantaneous power is kind of the easy one. And it really has some direct correlations with what we did before in DC power. Average power is slightly more useful to us. Instantaneous power gives us a function that describes the power, whereas average power gives us a number. It gives us something that we can hold on to and say, this is how many watts or how many whatever else that we've been consuming. RMS power is the one that I think is the most common if you're actually looking at doing power stuff as a concentration. You're going to spend most of your time thinking about RMS power, which is root mean square, and we'll talk a little bit about that. We'll use all of those powers, but primarily RMS power as we start looking at the power factor, the power triangle, and how to affect that power factor. Because, again, it has financial ramifications. If you can get a better power factor, your electric bill will go down. and that's a good thing. And then we'll look at complex power, which is very heavily tied to the power factor. We'll separate out the real power from the reactive power and look at their the individual influences of both of those. So let's think about a very simple series circuit. Nothing particularly interesting, but here is a circuit. It's got some sort of load on it. There's a voltage source over time. There is a complex impedance as a load, and therefore there is some kind of current over time. So what we learned way back in, was it chapter 1 that we actually, I think it was chapter 1, we learned that P equals V times I. And perhaps slightly more accurately, we learned that power as a function of time equals voltage times current as a function of time. Well, if we know that V of t is some function V sub m times the cosine of omega t plus theta, and the I of t is some current magnitude at a cosine of omega, we're going to call that theta v. I'm going to call this one theta I, because depending on what the load actually is, this may be a complex load, and if it does, then the theta v and the theta I are going to be different. If it's a wholly real load, then they'll be in phase. But as you've already seen doing some of that AC analysis, very quickly this can drive the voltage and current out of phase. Now, I think the full math for this is in the book, but you can, once you actually do this and you put it all together and you do all of the trigonometry for it, you get that the power as a function of time equals V sub m I sub m over 2 times the cosine of theta v minus theta I plus the cosine of 2 omega t plus theta v plus theta I. Now it's interesting to kind of dig into that a little bit. What you're going to get is, at least here, you've just got some sort of magnitude. This is just a number, right? And then this is the DC component, because that's going to be it's going to be a real number. Cosine of an angle, it's going to give you a number, and it's going to be scaled by the magnitude of whatever voltage times current over 2 is. Then the AC component, interestingly enough, actually operates at twice the frequency that the current and the voltage do, which is, I think it's interesting and somewhat unexpected if you sit down and think about it. It always catches me off guard to think that you've got this AC power, and we're trying to calculate as a function of time how you describe that power, and we've got a DC component and we've got an AC component, and that AC component is at twice the frequency of as the constituents, which is kind of interesting. But that's what the answer is going to be. You're going to get a function. And so if we were to put in some numbers into that, so for instance, let's say that we use the same basic little circuit, and we're going to say, well, let's let the voltage as a function of time be 4 times the cosine of omega t plus 60. And the complex load Z is going to be 2 at an angle of 30 degrees. And that must not have a particularly nice rectangular form. Yeah, I think it's something like the square root of 2 plus J1. But and so what if we want to find the instantaneous power? Well, the first thing that we need to do is we need to find out what the current is. And so we can write the voltage as a phasor as 4 at an angle of 60 degrees. So the phasor current I is going to be 4 at an angle of 60 divided by 2 at an angle of 30. Let's see what that works out to be. 460 divided by 230. I guess we get back the 2 at an angle of 30, which is an interesting choice. So that's the current that's rolling around there. And so it might be useful even now to turn this into a bit of or turn it back into a time function. And say, okay, so the current as a function of time is going to be 2 times the cosine of omega t plus 30 degrees. So now we can more or less just plug that stuff in. We have all of the information that we need. We can plug it back into our formula for instantaneous power and get the kind of the answers that we want. So power as a function of time is going to be the magnitude of the voltage, which was 4, times the magnitude of the current, which was 2, divided by 2, times the cosine of theta v, which was 60, minus theta I, which was 30, plus the cosine of 2 omega t plus 60 plus 30. And so obviously there's a certain amount of simplification that can go on here, a little bit of, I guess, trigonometry type stuff too. Obviously these kind of cancel out. Where did I get that number from? I have no idea. There's a magical 8 on my on my notes. But the 4 or the 2 and the 2 cancel out. The cosine of 30 degrees is 0.866 times 4. Gives you about 3.46 plus 4 times the cosine of 2 omega t plus 90 degrees. And that is the instantaneous power. And so you can find out at any given time what is the power. And this is, I think this is just calculated in watts. Well, I'm going to actually somewhat quickly introduce a new unit for measuring power that's will show up a little later, but I think originally this stuff is in watts. And so that, I mean, that is the answer, 3.46 plus 4 times the cosine of 2 omega t plus 90. But that's not a particularly handy thing to have. I don't know. I mean, I suppose it might be it's very accurate. It tells you at any given time what the power is going to be. And allows you to predict it and all that kind of stuff. But it's not really handy. It's not a number that we can just kind of use. We have to kind of come up with something a little better for that. And that's where it's what average power does. I don't usually ask a ton about instantaneous power because I figure that you can do some simple algebra and plug a cosine into your calculator. But you'll probably see one question on the homework that looks like that. So average power isn't as useful as it could be, I suppose. We would like something that is a number, something that we can walk up to our coworker and say it's 40 watts or 60 watts or whatever else. We'd like a number. And that's what average power gives us. There is an extremely long derivation in the book that tells us exactly why this is the case. But I'm going to skip all of that because I'm going to. And what it boils down to is that the average power in a circuit, what we're going to do is we're going to take that, it's the instantaneous power over some period of time, and we're generally going to define that period of time as being one period of our cosine function. So what that brings it down to is that you have the average power being V, the magnitude of the current times the magnitude of the voltage over 2 times the cosine of theta V minus theta I. And that's going to be your average power. It's a number that you can hold on to and say, here is the power. Wow, I totally was flashing back to He-Man and I have the power. And wow. You'd think it was a Friday with as kind of addled as my brain is feeling. But here is a number that you can calculate and say, here are some watts, and tells us what's going on. There's some interesting kind of ramifications here when we start examining this cosine term. What do we remember about the phase angles of the voltage and the current when they're both just totally a resistive circuit? Well, yeah, they're the same. And so the cosine, the theta V and the theta I are going to be the same. That difference is going to be 0. And what is the cosine of 0? Well, it's 1. And so essentially that term kind of disappears. And then if you have a circuit that is wholly real, there's nothing but resistors in it, then you can figure out what the the power is and ignore the cosine term. So this is again this is on the slides, but for real circuits or wholly resistive circuits, the power equals just V sub m I sub m over 2, because cosine of 0 equals 1. The voltage and the current are in phase. If you have a wholly resistive circuit, not resistive, but a wholly reactive circuit, something that is contains only resistor or only inductors or only capacitors, or it has to contain something that's the bottom line is that the phase angle has to, the difference between the voltage and the current has to either be negative 90 degrees or positive 90 degrees. And the cosine of those is 0, which means there is no average power. The average power for a reactive element is 0 watts. There's nothing there because the cosine of negative 90 equals the cosine of positive 90 equals 0. So that's average power. Now, normally our circuits are not going to fall nicely into just one of these two categories where it's entirely real or entirely reactive. And so what we're going to have to do is find out what is the relationship between the voltage and the current as a result of the combination of circuit elements that are there. But I could ask you a question, say, what is the average power absorbed by an inductor? And the answer is 0. It doesn't have an average, or it has an average power, and that average power is 0. That's what it happens to be. So how do you calculate that? Here's a simple example. Not terribly different from our first circuit, resistor, inductor. The voltage source is at 10 at an angle of 60 degrees. this is a 2 ohm resistor, and this is a J2 ohm inductor. So just in case it's hard to read there, the voltage is 10 at an angle of 60 degrees, and we want to find the average power. Well, we need to know what the current is that's going through it, because our average power, it says that it's V sub m, I sub m over 2 times the cosine of theta v minus theta I. Well, what do we have? Well, we have V sub m, we have theta v. We need to find out what I sub m and theta I are, or else we don't have anything to finish solving. So that phasor current will equal the voltage divided by the impedance. And so that's 10 at an angle of 60 degrees divided by 2 plus J2. 2 at an angle of 60 degrees divided by 2 plus J2. And gives us 0.707 at an angle of 15 degrees. And I think that's actually the square root of 2 over 2. It might help if I plugged in the right numbers. That shouldn't be 2 at an angle of 60. It would be 10 at an angle of 60. Sorry. So this is 3.54 an angle of... Ignore that. So now we have the magnitude of the current, we have the phase angle of the current, we can start plugging stuff in. Power equals the magnitude of the voltage, 10, not 2. Magnitude of the current, which is 3.54, divided by 2, times the cosine of theta v, which was 60 degrees, minus theta I, which is 15 degrees. So 35.4 divided by 2 is 17.7, 17 times the cosine of 45, which is 0.707, whatever. Gives you approximately 12.52 watts, and that is the average power that was absorbed by the circuit. Let's do, I got 2 more examples. I'll do one and we'll let you guys try one. So this is a negative J1 capacitor, a 2 ohm resistor, and a 4 ohm resistor. This voltage source is 12 at an angle of 45 degrees. And I guess as much for convenience sake, you can say here we generate some initial current I, and there's I1 and I2. And as we start thinking about what are the powers that are being absorbed by the resistors and capacitors and whatnot, we'll use those to keep the current straight as we start plugging it into the average power formula. Here in this case, one of the first things that we can say is that the average power of the capacitor equals 0. Kind of by definition. it's going to change the phase angles of the currents and stuff, so it's not, we can't just start ignoring it or anything like that. We still have to pay attention to it. But in terms of the power that's actually, average power absorbed by that capacitor, it's 0. So after that, we can just start saying, all right, well, that current I1 will be the voltage across the 4 ohm resistor divided by the resistance. Because it's directly in parallel with that 12 volt source, we can just do it. They have the same voltage across them. And we just do the division. 12 at an angle of 45 divided by 4 equals 3 at an angle of 45. And since we're working on it, why not figure out what the current I2 is as well? It's going to be that same 12 at an angle of 45. Again, it's in parallel with the voltage source. But we have to divide by the total impedance, which is 2 minus J1. So again, the point is that despite the fact that the average power consumed by the capacitor is 0, we can't ignore its influence on the circuit. It still changes the phase angle of at least of this branch of the current, which changes the average power that's going to be absorbed by this. Because had this 2 ohm resistor been isolated like the 4 ohm resistor, then no big deal. The phase angle is going to be 0, or the difference between the phase angles of the voltage and current is going to be 0, and we can ignore the cosine term. But we can't just do that because there is some reactive impedance here. When you run that, you get a much less nice number. It's 5.37 at an angle of 71.57 degrees, or thereabouts. And if you want to, I have it in my notes that if you add these two together, you can get what the total current was that was being generated by the circuit, but it's not a huge deal. So we should have everything that we need. We have a voltage, well, we have some of it. We know what the voltage is across the whole thing here, but we need to do like a voltage divider or something to figure out what's going on here. Or we can use our other version of calculating power as I squared R to figure out what the average power is. And either one should give you the same answer. Let's do this one first because it's nice and easy. We know what the voltage is across it. We know what the current is that's running through it, and it's just a resistor, so we can just plug stuff in. The power across that 4 ohm resistor will be the voltage of the magnitude of the voltage times the magnitude of the current divided by 2. So that's 12 as the voltage, 3 as the current, 2 is the denominator. 12 times 3 is 36, divided by 2 is 18. Now I'm kind of curious to see if I can get the same answer here. We should be able to do a voltage divider, and I want to see if this works. The voltage across the 2 ohm resistor is going to be some fraction of the original voltage given by 2 over 2 minus J1. So 2 divided by 2 negative 1 times 12 at an angle of 45. And so what I get is that is 10.73 at an angle of 71.57. I guess one reassuring thing is that we calculated the current in that 2 ohm resistor as being 5.37 at an angle of 71.57, and that should work out pretty nicely. The rounding is going to make this last digit a little weird, But otherwise, you multiply the voltage times the current, and you should get what that is. So we did a voltage divider. Obviously, you could also, if you want to know what the magnitude of the voltage is, multiply the current times 2. You should get the same thing both ways. And what made me feel good was seeing 71.57 as the phase angle in both places. The phase angle for the resistor should be the same, right? So the power in the 2 ohm resistor will be the voltage magnitude, which was 10.73, times the current magnitude, which was 5.37, divided by 2, which is 10.73 times 5.37, 10.73 times 5.37 divided by 2. It's about 28.81 watts, which I think is a little different than the answer in my notes, but it has to do with just rounding. It's only different down at the second decimal point. Now the way I have it done in my notes is using the I squared R methodology instead of the V times M, but you have to still include this denominator, the 2. So you could also calculate the power in the 2 ohm resistor as I M squared times R over 2, and that will also get you. I forget why, and I would have to double check and look a little bit further in the chapter. But you have to be careful about using the V squared over R methodology when you start dealing with complex impedances, and you have to stick with the I squared R one. And I don't remember the reason, but I'll check on that. Either way, you should get the same answer. This one, I think, actually, based on my calculators number and rounding, it came out to 28.84. So it's good enough. It's close enough for our purposes. So the total power being generated is just the average total power is the 28.81 plus the 18, which is 46.81 watts. And now I have an arrow on my hand. You guys feel ready to try one? Give it a rip. Shouldn't be too bad. Here's your voltage source. 12 at an angle of 60 degrees. Negative J 4 ohm capacitor, 4 ohm resistor, 2 ohm resistor. So find the average power consumed by each element. Take a couple minutes to work on that. So we got some of the work going on here, and you can catch up or finish up as you're feeling appropriate. The first thing to do is that in this case we need to know what the current is that's running through the circuit, kind of regardless. So the easiest way to do that is to first get rid of the kind of goofy looking parallel resistor and capacitor, turn that into an equivalent impedance. Maybe I hit my head harder than I thought on Saturday. Into an equivalent impedance of 2 minus J2. And so then when you want to find out the total current that's running through the circuit, I is the 12 volts divided by the total impedance seen, 2 plus 2 minus J2, which gives you 2.68 at an angle of 26.56 degrees. So now calculating the power in the 2 ohm resistor is pretty easy. You can calculate what the voltage is across it, but we have the current, and so we might as well just use it, that the magnitude of the current squared times the resistance itself of 2 divided by 2 gives us the total power. And obviously these two kind of cancel out, and the square root, and 2.68 squared is 7.18. So that one's not too bad. After that, we have to do a little bit more work to figure out what's going on. Because either, well, we know that what the current I is that's coming here, but then I divides between these two branches of the circuit, so we're going to have to figure out what that current is. Let's stick with the same kind of idea and do a voltage divider. The power absorbed in let's call it the current in the 4 ohm resistor. It's just doing current division, so we're going to use the other thing on top, the other impedance, negative J4 over the total impedance, 4 minus J4, times the source current, which we calculated already was 2.68 at an angle of 26.56 degrees. Plug all that good stuff in. So negative J4 divided by 4 minus J4 times 2.68 at an angle of 26.56 degrees. This is a current, so we kind of like to have it in a polar form. And I'm getting a slightly different answer than I did before. Got the right phase angle on that current? 12 by 4 minus 2. Yeah. Oh. It would help if we did that and actually used the right phase angle on the voltage source. That's not going to change this calculation because we're strictly using the magnitude of the current, and that changing the phase angle isn't going to change the magnitude, but it will change the current, or change the phase angle of the current to not 26.56, but rather 86.56 degrees. So we change that down here too, and that will get us the proper current, 2.68, no, not 2.68, 1.89 at an angle of 41.57 degrees. So now we have the current. Power in the 4 ohm resistor will be that current squared, Im squared times R divided by 2, which is going to be 1.89 squared times 4 divided by 2. 1.89 squared times 4 divided by 2, 7.14 watts. Again, the power in the 2 ohm resistor had been 7.18 watts. And the power in the capacitor is 0, at least the average power. Any questions on average power? No, I want to see another one or anything like that, or? Okay. The next concept is effective or RMS values. Again, RMS stands for root mean square, and that gives you an idea of what it is exactly you're going to do to kind of calculate what an RMS value looks like. Instantaneous power is obviously very useful. It gives you a function that always tells you exactly what the power is that's being consumed. And average power seems a little bit more useful because you have a number. You can hand someone, say, 7.14 watts. That's how much is being absorbed on average. But effective values or RMS values are the most frequently used, as far as I know. If you were to go grab a light bulb and look at the top of it, or if you've got one of the old evil incandescent bulbs and you haven't switched over to compact fluorescence yet, I guess, it usually says something about 60 watts RMS, and that is it's saying, effectively we're using about 60 watts. And the idea here is to kind of say how effective are we doing our transfer of power, or what is the equivalent in DC, if we were to kind of almost abstract away the idea that we are using AC current. At some points I looked up a little bit more information about root mean squared, and for the math types, if you consider x bar to be the average of a given function, specifically the arithmetic mean, and if little delta x is the standard deviation, then the RMS value squared equals the average value squared plus the standard deviation squared for that. I don't know if that means much to you, or if that makes it explicitly clear exactly what the relationship is to root mean squared, but that is, mathematically speaking, what the RMS value is. It's kind of a combination of the mean and the standard deviation. That's more a parenthetical aside than anything, and maybe it makes you a better person, I don't know. A more effective way of calculating the RMS value is using this function, and you can see each chunk here. And you do these kind of almost in reverse order. So we start out by so here's a current. That's what we're looking at. First we square it. Then the integral with the period of t gives us the mean over some period of time, and then we take the square root of it. And so that's, here's the r, here's the m, here's the s, root mean squared. And you actually perform the operations kind of in reverse to get to that number. For a sinusoid, you can go through all of the calculations, cosine squared, integrate over time, take the square roots, and what you get essentially is that things don't change with the phase angle or anything like that, but the magnitude is slightly different, so such that if you divide the peak value, that's what we're going to start calling I sub m, is the peak. Then you divide that by the square root of 2, and that will give you the RMS value. And again, interestingly enough, when you start looking at stuff in the wall socket, most people know, well, it's 120 volts, but that's 120 volts RMS, and which means that the peak value is actually 170 volts. It's an extra 50 volts when you start shoving that paper clip into the wall or whatever. And so that's the kind of the simple relationship between the two. And it's important to make sure when you are using RMS values and when you're not using RMS values. And that was one of my biggest problems in power class, was figuring out when am I using an RMS value and when am I using a peak value. So make sure you pay attention. Are you using a peak value or are you using an RMS value? And for sinusoids, it's pretty easy because we can just divide by the square root of 2 or multiply by the square root of 2 to get the peak value or get the RMS value depending on which direction we're actually going. So again, there's a fairly complicated proof that that's the case, but kind of suffice it to say that the square root of 2 is our magic ratio here. I will do one of these real quick because I think that they're not particularly interesting problems, but let's say that we have, I want to do this at least once. In the past, we've skipped over all of these kinds of questions with the integrals in them of waveforms because I think that you're capable individuals. But let's say that this is we'll do at least one of them. Here is our voltage as a function of time. Kind of an interesting and irregular sawtooth. So if this is the voltage waveform, this is time 1, time 2, time 3, time 4, time 5. This is voltage on the x-axis. This is time voltage on the y-axis, time on the x-axis. The magnitude up here is 4. The magnitude down here is -4. And that, in a very straight line, connects right there, obviously. And what that means is that as a piecewise function, a periodic piecewise function, that it equals 4 times t for time 0 less than or equal to t less than or equal to 1. Then 0 for time 1 less than t less than or equal to 2, and then -4t plus 8 for time 2 less than t less than or equal to 3. So that's the piecewise representation of that, and it's fairly straightforward, I think. So the whole period of this function is 3 time units. That's how long it takes for it to do it's up, it's flat, and it's down. So that's going to be our period. Our 1 over t in our RMS calculation is going to be 1 over 3. So the whole calculation here, so we say, all right, square root of a big mass. Period is 3, so it's 1 over 3. And then we've got a bunch of integrals, finite integrals, fortunately, from 0 to 1 of 4t squared. I guess there's a dt in there. Plus 1 to 2 of 0 squared. Oh, I can do that one. Plus the integral from 2 to 3 of negative 4t plus 8 squared. So squared, all the terms are squared, and you have to make sure that you do that first, or else you're not going to get the right answer in terms of figuring out what the RMS value actually is. So obviously that's going to be the square root over the period here of 16t cubed divided by 3, evaluate from 0 to 1, plus, well, the integral of 0 is 0 squared, 0 I suppose we can say 0 evaluated from 1 to 2, but that's kind of silly almost. And then the slightly more nasty part, which is 64t minus 64t squared over 2 plus 16t cubed over 3 evaluated from 2 to 3. And it's just expanding all that junk out. Yeah, times the whole stinking thing. I guess all of the additive terms here. So you go through, you do that, you do your 16 times t, so 16 divided by 3 minus 0 plus 0 plus, and do the whole evaluation thing. Divide by 3, do the square root, and what you get is 1.89 volts. And so I guess the nice thing about RMS in this case is it's allowed us to kind of, again, take something relatively complex, like this kind of goofy, piecewise, almost sawtooth waveform, and quantify it as just a number. Yeah, it's 1.8 volts. And usually we'll tack on a VRM, or a subscript of RMS, to make sure that it's very clear that what we're dealing with is a root mean squared value and not a peak value. In my notes I have a couple more examples of this, and it's always the same thing. Do this integral over a finite period of time, divide by the period, take the square root. And I think that you guys are pretty capable of doing that kind of thing. It's not particularly difficult. There is one thing that there's kind of I don't know how I got rid of this in the original slides, but I need to fix this at some point. We said that the magnitude of, there's this relationship of the peak voltage to the RMS voltage by dividing or multiplying the, we can multiply the RMS value times the square root of 2, and that gives us the peak value. Same thing is true for the magnitude of the current. Multiply the RMS current times the square root of 2, and you get the peak value. So we can go back to our average power formula, which was P equals V sub m R sub m over 2 times the cosine of theta v minus theta theta I. Wow, that got messy. And we could plug in these things, the RMS values, and say, all right, well, that's VRMS times the square root of 2, and IRMS times the square root of 2. And well, the square root of 2 times the square root of 2, I'm pretty sure that equals 2, and that cancels out with the 2 in the denominator, and so all that kind of just goes away, and you're left with just VRMS times IRMS times the cosine of the phase angle of the voltage minus the phase angle of the current. And I think that's still right. This term is what we call the apparent power. And for reasons that I've never fully looked into, to give you a good reason, we measure this in volt amps instead of in watts. I don't know. It's just kind of another weird tradition. We always do the impedance in rectangular form. We always do voltage and current in phasor form. We always measure apparent power in volt amps. It may have something to do with making sure that we don't claim that it's a watt, but dimensionally a volt amp is a watt, so I'm not sure what the deal is. Maybe I'll try to find that out for you. But and so the unit abbreviation is VA next to each other, and so you can have like 110 kilovolt amps or something like that. And one of the next things that we'll find is that there's also a unit called volt amps reactive, or VAR. So we'll see that in a little bit. This part is something that we're going to define as being the power factor. And this specific part, which is the difference between the phase angle of the voltage and the phase angle of the current, we're going to call that just the power factor angle. And what we will see is frequently this will be called theta ZL, sometimes theta PF, something like that. One of those abbreviations will be for the power factor angle. And so if you ever know the power factor angle, you can calculate what the power factor is given the cosine. You can perform an inverse cosine on the power factor itself to get the power factor angle, which gives you the difference between the voltage and the current. You have these relationships, and you can start messing around with them as you see fit, or as you see necessary, I guess. A little bit, I think we'll have about enough time to just kind of talk a little bit more about the power factor angle. So if we can look at the PowerPoint slides. Power factor angles then can be anywhere from 0 degrees, which would be for a purely resistive load, up to 90 degrees, which would be a purely reactive load. Again, because the power factor angle is just going to be the difference between the voltage and the current. And if you have a purely resistive load, there is no difference between them. And if you have purely reactive, it could be 90 degrees. It could be positive 90 degrees. It could be negative 90 degrees, whether you're looking at an inductive or a capacitive load, right? or some mixture of the two. Therefore, based on the fact that the power factor angle is somewhere between 0 and 90, at least in terms of its magnitude, when you plug that into the cosine function, you should get a number that's somewhere between 0 and 1. If you have a purely reactive load, the cosine of 90 degrees is 0. So that is a enormously bad power factor, let's put it that way. If you have a purely resistive load, you have a power factor of 1, which is called unity. And the closer that you can get to a unity power factor is better. Now, however, it is not, strictly speaking, entirely the case that you can't have a circuit that contains an inductor or capacitive elements and still have a unity power factor. And it has a lot to do with the fact that you can have inductors and capacitors kind of playing off against each other, which will kind of cancel out the influences of the other one. And so one of the final things that we can do is, because those capacitive loads will have negative phase angles, the inductive loads will have positive phase angles, we have to differentiate between the fact whether the power factor is leading or lagging. And normally what we're gonna see is it's going to primarily be an inductive load, because industrial loads tend to be inductive. When you get especially into like your DC motor or your motors class and stuff, you're gonna see motors, AC motors, DC motors, heavily inductive looking loads, and those are going to create primarily lagging power factors, and so we're going to want to try to correct those back up. We'll finish talking about this stuff tomorrow, start looking at complex power. Exam is at 6 o'clock tonight. If you have any questions, please let me know. Otherwise, have a good evening, and we'll see you later.